Hello, it's Keith here, and this is lesson 7 of the platform-specific series of my 6502 assembly tutorials. We looked at the NES last time, and now we're going to move on to the Super Nintendo, also known as the Super Famicom. Now, the clever ones among you might say, hang on a minute, that's not a 6502, that's a 65816. Well, yes, you're right, but the 65816, the 16-bit processor, is backwards compatible and starts in 6502 mode. So we are going to treat it as a 6502, and my Grime 6502 game never used any 16-bit operations and was able to play a basic game. So that's what we're going to look at in this series. Now next year I'm planning to do a 65816 assembly tutorial series, but for that we're not going to be able to use VASM because VASM can't support the 16-bit commands. So for starters we're just going to look at the 8-bit processor, the 6502. We're going to look at how to use the commands in 8-bit mode, and then we'll extend to 16-bit later next year. So that's out of the way, let's start looking at the actual machine. Now, just like the Nintendo, the Super Nintendo uses a PPU. It's a different PPU, of course. The Super Nintendo was intended to be backwards compatible with the NES, which is why it uses that 65816 processor, but they abandoned the backward compatibility, so the actual hardware is completely different, but that's not particularly much of a problem for us today. So we've got some memory mapped registers. We've got a whole bunch of them here. This is just a small selection. On my website, there's a much bigger list, which is all of the registers, but the vast majority of them we'll never need in these tutorials, and there's very few we need for graphics. We're going to come to them later though. This is just for your reference here. Now, once again, the PPU has its own dedicated video memory, and just like on the NES, we address that memory by selecting the destination and then writing data to it. Now, the addresses would look like 8-bit addresses because we've just got 2 bytes defining the address here, but the rather odd thing on the Super Nintendo is that each of these addresses actually holds 2 bytes. So we write a pair of bytes to each address, and so when we increment the address, we're actually moving along by 2 bytes, and this makes things a little bit confusing because we are using the same number of addresses, 16 addresses per tile when we're defining our tiles, but the tiles are now 4 bits per pixel compared to 2. So a bit strange there, but that's really just the way it works. We've got a structure for our tile map here. Our tile map we're going to define at the memory address 0, so that's where our tile map's going to be, and each address holds 2 bytes again. Now, the Super Nintendo supports up to 1024 tiles in theory, so we've got a lot of range there. We've also got the option for up to 8 colour palettes. We've got vertical and horizontal flipping, and the tiles can be set to be in front of or behind sprites. As with the other lessons, we're not going to use sprites today. We are going to look at them later on though. So all we've got here is some very simple introduction information for reference really. We're actually going to, as always, look at the source code and do things from there. So let's go over to our source code for today's lesson. Okay, so first of all, let's just see the program running then. And so, as before, we've got some text on the screen and we've got our Chibico character here. So this is what we're doing every time. We're showing the Chibico character. This is a bitmap that we've got. And as always, this was created with the AccuSprite editor. So here's the AccuSprite editor, and I've been doing some font work for my Chibi Aliens game here. So we'll just go to our tutorial bitmap graphic here. And here it is. So this is the bitmap graphic that we're looking at today. And if we want to export, we just go to the processor up here and we select Super Nintendo, and we've got a save raw bitmap option. All of the systems covered in my tutorials today and in the future are going to be supported by the AccuSprite editor, and the AccuSprite editor is free and open source. So if you're interested, download it and do whatever you want with it. So that's what we're using today to create the graphic for today. You've seen the graphic working. Let's have a look at what it actually takes to get that graphic onto the screen. So the first thing we're going to do is we're going to initialize the screen. Now, to get the screen working, we need to set up quite a few registers on the Super Nintendo, so a little bit of a pain, but most of them are fortunately fairly generic. Now, the position of the tile maps can be relocated in memory, so the first thing we're doing is we're setting the position and the size of the tile map. Now, in these tutorials, we're just using a 32 tile wide tile map, which isn't really going to allow for scrolling. It is possible to use larger tile maps, and that would allow for more efficient scrolling, but at this stage, we're not looking to do any scrolling. Grime 6502 didn't use any, and as a basic beginning game, that's kind of what you're probably going to be wanting to aim for. You know, you're not going to be doing anything too advanced in the early stages. So this tutorial is set up for a 32 by 32 tile map because that's common to all of the systems. Next, what we're going to need to do is actually turn on the screen. Now, the Super Nintendo has 4 different layers because it can do parallax scrolling very efficiently. So we're just turning on the first one here, and it also has a sprite layer. The sprites are turned off in this example so far. We're going to look at sprites in a later lesson. Then we need to turn on the screen, and we need to set the brightness of the screen. It has a brightness option, so we're setting it to maximum brightness. Next, we've got the definition of some colors here. Now what we're doing here is we're selecting the color register we want to change, and then we're sending an RGB combination here. We're not going to look too much in colors in this lesson because, as with all the other systems, we're going to cover colors separately in a later lesson. So there we go. Okay, so we've now set up our colors, we've set up our tile map. Now it's time to actually set how we're going to increment the memory. Now we have 2 different ports that we use to write data, 2118 and 2119. These are used for the 2 bytes that, as I said before, are stored in each memory address. And so what we need to tell the system is, when I write to this address, increment the address register to point to the following address. So we can increment on the low byte or on the high byte. We have that choice. So we're going to increment, in this example, on 2118. So that's what we're doing. And then finally, we're setting the screen mode here. Then we've got a load of the font. This is converting our 1 bit per pixel font into tiles that are loaded into the first 128 tiles in the tile definitions. Now we're setting the scroll position. We're setting the screen so that the 0 byte of the tile map is in the far left of the screen. That's what I use in my tutorials. Now on the Nintendo NES, we often had to reset this whenever we wrote to video memory. On the Super Nintendo, we also have the problem of having to be in Vblank when we write to video memory, but we don't ever need to reset that scroll location. So that's something that's a bit of a plus. You can see our wait Vblank command here, and another plus is that the wait Vblank command is much simpler. On the NES, what we were doing is we were reading a 0-page entry and waiting for that 0-page entry to change, and the Vblank would have a changed programmed in the interrupt handler to change that registry. The problem is, what was happening is we were having to wait basically for an entire Vblank every time we wrote to the screen. In the very basic example, we looked at a later one that used a buffer. This example is much cleverer. It's actually polling the hardware and seeing if Vblank is currently occurring. So if we do 10 commands and they're all in Vblank, they will all occur just fine. That said, the Vblank routine here isn't ideal. We're still using a basic example here. This V1 file isn't perfect. We're going to use a V2 file later today, and that is going to use a buffer again. And this all came from Grime 6502, my programming series. And in the early days, I was using this basic code. It worked okay, but there was the odd glitch on the screen, presumably as the interrupts were kind of misaligned. You know, maybe Vblank was on when I started writing, but off when I ended or something like that. So I ended up using a buffer, and we will look at that as well. But this wait Vblank command will effectively wait until Vblank is occurring. So that's how we get our screen set up and ready to actually draw some graphics to it. So let's have a look at our bitmap test routine here and see what we're actually doing to get that Chibico bitmap to the screen. If you've seen the NES series, this is going to be very boring to you, but I'm assuming you probably haven't, so I'm going to go over it all again. It's quite short anyway. So we're loading the source memory address of the data. That's the bitmap data from AccuSprite Editor, and we're loading that into a 0-page entry called ZHL here. So I always simulate the Z80 registers using 0-page addresses because it's the way I tend to think. So we're using H and L here as the source address. We're using B and C as the length of the data, so that's the length of the bitmap we want to copy. Then we're using the address of the data here, and we're loading to 1800 in hexadecimal again, which is exactly the same as the PC Engine. Now, that's really a coincidence. The thing is, unlike the PC Engine, the tile data within the Super Nintendo starts at hexadecimal 1000. Now on the NES we were starting at 800 because it started at 0, but the quirky thing is, because each address holds 2 bytes in the Super Nintendo, the offset is still a hexadecimal 800, even though the Super Nintendo uses twice the bits per pixel as the Nintendo did. So that's a bit of a quirk, but as I say, hexadecimal 1800 is effectively 128 tiles in the Super Nintendo's tile definitions, and the first 128 of course used by our font. We've got a command here called define tiles. This defines tiles. What it does is it transfers the bitmap data, which is already of course in Super Nintendo format, thanks to AccuSprite Editor. It converted it for us, and we're transferring that into the Super Nintendo's tile data. Now we define an XY pos in tiles, and we define a width and height in tiles, and we use the fill area with tiles command. This copies our Chibico character onto the screen. You see each tile is 8 by 8, so this is being split by AccuSprite Editor, so this would be tile 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and so on. And fill area with tiles is recombining that tile map onto the screen so our Chibico character looks as it should. And that's what we're doing. So of course all of the work is really being done by define tiles and fill area with tiles. That isn't being done by the AccuSprite editor, of course. So let's have a look at those commands. So the first command is define tiles. What does this do? Well, it calls a command called prepare VRAM. What this does is it selects the destination memory address we want to write to. Selecting that is very straightforward on the Super Nintendo. We just have two ports, 2116 and 2117. 2116 takes the low byte of the address, 2117 takes the high byte of the address. This selects the address we want to write to. Now you do have to notice that each time before we write to the tile definitions we do have to wait for Vblank, and we also have to wait for Vblank before the prepare VRAM. Any write that occurs to the Super Nintendo video memory has to wait for Vblank before it can occur, and we're going to find a workaround that makes this a lot easier later using a buffer. Now we want to send our 2 bytes to the data. Remember we were writing in byte pairs here. Now I've selected the address to increment on the write to 2118 here. So we read in a byte from the address held in the 0 page HL, and then we write it to 2119, we read in a second byte, and we write it to 2118. Now we decrement BC twice and increment HL twice, and we're decrementing BC twice just to maintain compatibility across all the systems because we're using the same definitions on all of these systems. These are multi-platform tutorials, so sometimes that's not really that efficient. You'd probably want to halve it and just decrement it once for the SNES, but as I say, I'm trying to make everything common so that we can write for lots of systems at the same time. So that's what we're doing, and of course once we've written to this address, the address that we specified here will automatically increment by 1. So all we need to do is loop back again and keep defining data. We don't need to ever select the VRAM address again. So that's how we're writing our tiles. Once this command executes, our tiles are defined. The next command we need is fill area with tiles. What this does is it actually sets the tile numbers within the tile map. So how do we do this? Well, first of all, we use the command get VDP screen pos. Let's take a look at that. What this does is it calculates the memory position of the tile number that we want to select. The tile number is in ZB and ZC and in XY position. So all we're doing is we're multiplying the Y position effectively by 32, and then we are adding the X position, and that is effectively our tile number, and that is effectively our position in the tile map. Now if you remember, the tile map that we're writing to starts at memory address 0, so we don't need to add any kind of offset to get to the tile map. What we do need to do though is wait for Vblank. Now as before, we need to wait for Vblank, so we're calling the wait Vblank routine here, and then we are writing our low byte of our memory address that we want to write to, and then the high byte just here, and that has selected the memory address of the tile within the tile map that we want to change. This then brings us to here. Now we're going to do another wait for Vblank because Vblank might have ended by the time that that last command completed, and then we're going to write the 2 bytes that make up the tile definition that we want to show on the screen. Let's have a look at that format once again. So we write 2 bytes. The top byte is the top 2 bits of the tile number, the palette number, and the horizontal vertical flip, and the layering, whether it's in front or behind of the background. Now in our example, we're only using tiles up to 256. So we're writing the top byte as just a 0, so we're effectively selecting no flip, no palette number 0 that is, and we're selecting the bottom tile as being 128 to 255. It's only a basic example here, we're only supporting up to 255 tiles, again, because we're multi-platform and the NES and systems like that can only do 255 tiles, so just keeping things consistent there. So we then loop around here, waiting for Vblank each time, because we never know when Vblank's going to end, and we just repeat. Once we've done a line, we repeat back here, recalculate the starting position of the screen, and that should do us. So that's how we're getting the tiles onto the screen. And, you know, it does work pretty well. Let's just run it again. So, you know, it works okay. It's not perfect, but it's a little bit slow maybe, and as I say, with Grimes 6502, it didn't work ideally. So there were occasional graphical glitches. So what I'm going to do now is I'm going to turn on this function here called useNetsBuffer. This is going to turn on our more advanced mode. Now, hopefully you saw there that was a little bit faster. Let's actually take a look at what the code has changed. And I'd have noticed that O was actually missing from the last one. It said Hell Worlds, which apparently it wasn't supposed to do. And I think maybe that was a glitch with regards to the interrupts were actually missing one of the writes, which was the problem Grimes 6502 had. Let's have a look at what's actually changed. Well, What are we doing differently now? Well, what we are now doing is we've defined a buffer of memory, which is effectively the entire tile map. All 32 times 32 tiles that select the visible tiles are now being stored in memory, and that memory is being transferred during the interrupt into video memory in one burst during the Vblank. So we no longer need to wait for Vblank, and we no longer need to worry about any kind of Vblank issues if there's glitches. So that's what we're doing. And whereas on the NES we were having to do that as a manual data copy, the Super Nintendo has a really good thing for us. It has something known as a DMA. A DMA is known as direct memory access. This is where the hardware itself goes straight to the memory and does the work for us. So we don't need to do anything else except for say, DMA, do your job. Now the Super Nintendo DMA actually halts the processor and transfers the data. So as soon as the command finishes, so as soon as we tell the command to execute the DMA command, as soon as we get the next processing command to run, the DMA will have already finished. And because we're only copying a very small amount of data, relatively speaking, it's going to be basically instant. Some DMAs would run concurrent to the processor, you see, like the sound DMA on the Amstrad CPC. That will actually play while the BASIC is running and things. But in this case, it's not like that. So all we're going to need to do is specify the source data and start the DMA. And we're going to have a look at that. But we've got a kind of summary of the various commands and options we've got here. We're not going to need most of them, though. So now in this case, we're now using this V2 version here, the Super Nintendo V2 version, which uses the buffer. Now, the introduction code, the init routine is identical. We've still got the wait Vblank, but we hardly need it now. We have this custom NMI handler here. We're going to look at that in just a moment. What this is doing is it's copying the SNES buffer. We've got this defined here, and this is being defined in RAM. And so this is going to be the size of the entire tile map, and we're going to copy it across. Now in this example, the define tiles routine does not use the buffer. It's still writing back in the exact same way. The reason for this is I didn't think it was worth it. I was figuring that you're probably defining your tiles at the start of a level or the start of the game, probably when the screen's even switched off. So I didn't think it was worth using that buffer at this point just to get the data transferred directly. But then when it comes to the fill area with tiles command, we are doing things very differently. We've got our get VDP screen pauser command again, but here now you'll notice it's calculating, but it's no longer calculating an address within the video memory. It's now calculating a byte within the screen buffer. So the calculation is slightly differently because we're counting in bytes rather than words. But apart from that, it's pretty much the same. And we're now storing the destination address in the HL pair here in the 0 page. And we're then using that 0 page pair here when it comes to actually writing our tile number. So we're storing our tile number here. We're storing the low byte, then the high byte. So we're in Little Endian this time. And that means we're storing the tile number that we want to show during the next Vblank within that buffer. So that's where we're using our buffer. Now, how do we actually get that buffer to the screen? Well, we have this function called custom NMI handler. How do we define an interrupt handler on the Super Nintendo? Well, it comes down to the end of the cartridge. If you look in this footer here, this is the top few bytes of the 64K range, and this is the basic entry of our cartridge. So we've got some header information here, which you shouldn't need to change, but then we have these jump vectors here, and the one we're using is this one here, the Vblank one. We've got two versions. We've got a 6502 version for when the CPU is in 6502 mode, and we have a 16-bit version for 65816 mode. And we're going to be, of course, working in 6502 mode, but I've put it in both places just for completeness. So whenever an interrupt occurs, a Vblank interrupt, it's going to jump to custom NMI handler, which I've defined just here. This could happen at, of course, any time during the game playing or whatever our program is. So we need to back everything up. So we're pushing the processor flags, then we're pushing all the registers, and now we're going to start actually doing some work. Now the first thing we're going to do is we're going to set the destination address to 0. Then we're going to set to increment on 2119. We were incrementing on 2118, but we want to work from 2119 this time. Now we're going to set the DMA's writing mode. We're going to write to two alternate memory addresses because if you remember, we're writing to 2118 and 2119 alternately to write our bytes into video memory. So the DMA on the Super Nintendo is obviously directly programmed to just work with the Super Nintendo's requirements, so it can write in that special way to get data to video memory quickly. We're then going to tell it the destination we want to write to. We want to write to 2118 here, so we're writing hexadecimal 18 here to 4301. That sets the destination address of the DMA. And of course we're going to write to 2119 as well because of that alternation. Now we're selecting the source address. The source address is 24-bit because the 65C02 has a 24-bit address bus. So all we do is we set the low byte to 4302, the low byte of our address buffer, for the high byte to 4303, and then a 0 to 4304 because we have no top byte. We're only using the first 64K of our memory here. We've now selected the source data. What we want to do is select the byte size now. We're using a 32 by 32 tile map, and there's 2 bytes per tile. So we're just calculating that here and writing that into the 3 bytes here, again with the top byte being 0. We now need to set up the kind of write we want to do. We're disabling something called HDMA. This is a DMA. I believe this works during the horizontal blank between lines. That's not something I think there's going to be particularly much use for, so we're turning that off and we're enabling the normal DMA. When we enable the normal DMA, the process immediately occurs, and as I said, the processor won't do any commands before it occurs. So the first thing we're doing is we're turning our increment back to 2118 here, and that won't affect the DMA because it's already finished by this point. We then pop all of our registers and restore the flags of the register and just return with the RTI return from interrupt command. So that's the job done, and as you can see, it works pretty well. And this is the code that was used in Grimes 6502. And as you can see, that works pretty well as well. So there you go. That's how we can get bitmap graphics very simply to the Super Nintendo just by using the tile map. We're going to learn sprites at a later date. So there we go. Actually using the Super Nintendo isn't too bad, despite the fact that it's a 16-bit processor with all kinds of weird commands. If we're willing to sort of sacrifice that and just work in 8-bit mode, we can get some pretty decent stuff working on it without too much work. Now, one other thing I suppose I should tell you about is the actual format of the tile map. Now, if we're going to write our own tiles without using AccuSprite Editor, and of course I had to do this to get AccuSprite Editor working, we need to understand the format of the tiles. Now, just as before, we have to write in byte pairs in words to the video memory. And the way it works is the first byte we write is the first bit plane of the first line. The next line we write is the second bit plane of the first line. And then that repeats for all of the 8 lines of our tile. And then we continue with the third and fourth bit planes. It seems very strange, but that's the way we actually have to write it. As I said, if you're using AccuSprite Editor, you don't need to worry about that. But I just thought I'd better bring it up as a sort of finishing note, just in case you're really deciding to go hardcore on it and do all of this yourself. Anyway, I hope you found this interesting. We're going to be doing lots more on the Super Nintendo and, of course, all the other 8-bits as well. So, please follow along. And if you enjoyed this episode, please share it on the social networks because that brings a lot of new people to see my videos. Anyway, thanks for watching and goodbye.